Hello AP Stats students, this is Mr. Hazelhorst here with your second video over Chapter 2. Today we're going to talk about the normal distribution and the standard normal distribution, which are going to be two very important density curves that we focus on utilizing a lot, not only here first semester, but especially second semester when we get to our different statistical inference procedures that we can utilize to really analyze some data deeper than what we're going to be able to do here first semester. So this is a concept that we really want to buckle down on and make sure that we have a firm understanding of because again it's going to be foundational to a lot of the different things that we do here in AP Stats. So take some time here over the next couple of days, not only through this video but also the time that we spend in class, and make sure that you have a firm understanding of the normal distribution because again we're going to utilize that a lot. But let's jump into the characteristics of the normal distribution and introduce you to a few different concepts related to it. So here we see an example of what a normal distribution looks like. It's got a few main characteristics. It's symmetric, perfectly symmetric when we talk about something that is exactly normal. It's unimodal. We can see that it's only got one peak there. And its shape is determined by the mean and the standard deviation. Now I want to make note of the symbolism here. We introduced this the other day in class, but I want to make sure again that we recognize the symbols that are being utilized here. So the shape of a normal distribution is based on the mean of the distribution, which we're using that Greek symbol mu again, which means that it's a population mean. It's a mean based on a density curve. And it's also determined by the standard deviation. And notice again the symbolism that we're utilizing here. We're utilizing that lowercase sigma. So again, Greek letter sigma, and again representing the standard deviation of a density curve or a population. And those are important symbols that we want to recognize the difference between. As we compute things, again, we're going to utilize x bar and s, but in a density curve or normal setting, we're utilizing mu and sigma. So keep that in mind. All right. Now, a normal distribution will take on all these characteristics, but it might change a little bit again based on its shape. So something that's got a large standard deviation, that would be scrunched down. It wouldn't be as tall, but then it would be wider because remember, all distributions, all density curves have an area of 1 underneath it. So if we're going to make this distribution not as tall, we have to widen it out to again represent that area of 1 underneath that curve. Now the standard normal distribution is what we utilize when we use a z-score in any setting. And sometimes when we utilize a z-score in a standard normal distribution, that's known as standardizing. But what we're doing then is we're saying, okay, the mean you are 0, the standard deviation is 1, and when we standardize things, we're not representing the values of the data, but instead we're representing how many standard deviations something is away from the mean. So if I have a z-score of 1, that means I am 1 standard deviation above the mean, since I said positive 1 there, and so on. So we want to keep those things in mind. The difference between the normal distribution and the standard normal distribution. A normal distribution can have any mean or standard deviation. The standard normal distribution will always have a mean of 0 and a standard deviation of 1. And over the next couple of days in class, we'll spend some time doing quite a few different calculations utilizing the normal distribution and the standard normal distribution. And you're going to see the work between the two is very much the same. All right, but now let's introduce a very important characteristic of the normal distribution and something that we'll build on later. Now, I mentioned before that statisticians aren't very creative in the names that they come up with for things. And here we see another example of that. What we're going to introduce you to next is what's known as the 68, 95, 99.7 rule. And this is something that holds true on any normal distribution, anything that's normally distributed. So what that means is all normal distributions have 68% of the data within 1 standard deviation of the mean, 95% of the data within 2 standard deviations of the mean, and 99.7% of the data within 3 standard deviations of the mean. Now, notice that it doesn't contain 100% of the data within 3 standard deviations, but there's not very much data that's going to get beyond 3 standard deviations of the mean. So to be beyond 3 standard deviations of the mean, you're really starting to get into what we would consider that outlier phase. You're getting considerably far away from a majority of the data. And so this is something that we want to understand. This is something that we'll utilize as we do some calculations here the next couple of days in class. But it's a very important characteristic that, again, is foundational to a lot of what we're going to do here in AP Stats. So we want to remember that 68, 95, 99.7 rule. And again, those numbers are representing the percent of data that are within those whole number standard deviations from 1 to 3. And so again, we want to keep this rule in mind as we move forward here in class. Now, we're not going to focus on any calculations in this video. That's easier for me to represent in class as we do some examples. We're going to introduce you how to do calculations using a chart in your textbook and in a resource packet that you'll be receiving soon, and also on your calculator. And so we're going to save those calculations for in class. But I do want to talk about one more really important concept about the normal distribution. And this will be something that we don't utilize a lot now, but will be important down the road. So the sooner we can introduce it and start to become familiar with it, the better. Now I have a couple of really important thoughts for you. And again, this may not click here right now, and that's okay, but I want to introduce this concept because it's going to be really important down the road. Second semester, when we start to introduce the idea of statistical inference, a majority of the procedures that we are going to use to analyze data are going to be based on the assumption that a population that we're analyzing is normally distributed. Now, a lot of times people will assume then, well, if that's what I'm supposed to have as a normal distribution, they'll just assume that everything is normally distributed. But we have to be very, very careful that we don't assume that something's normally distributed without actually inspecting the data first. So that's what I want to talk about here real quick, is how do we assess data for normality? And that's going to be a phrase that you start to hear more second semester. But again, the sooner we can introduce this concept, the better. So there's 2 different ways that we can assess for normality. And it fits well here because we've just come out of chapter 1 where we've talked about a whole bunch of different types of graphs that we can utilize. And so one of the methods that we can use to assess for normality is that we can actually analyze the graphs of the distribution. And we'll look at that here in a moment. The second is through the use of what's known as a normal probability plot. So we're going to introduce this concept here to you today. The good news is our calculator can draw normal probability plots for us. It's just our idea, or it's just our job to know how do we interpret that correctly, how do we recognize when something truly is normally distributed. Because again, we want to apply a normal distribution only in situations where it's appropriate to be used. So let's talk about assessing normality based on analyzing graphs first. So our first method for assessing normality is to look at graphs, and histograms and stem plots are the 2 types of graphs that we utilize the most often here as we talk about looking for normal features or non-normal features. So features that we're going to consider non-normal, you can see listed out here. Things that are considered outliers would be an example of something that's a non-normal feature. If we have a real strong skew, that's a non-normal feature. If we have gaps in our data or clusters, where all of our data just falls in a couple of groups, we really don't have that data that's kind of tailing out to the left and the right. So here we have 2 examples of different graphs. Let's start out with a histogram at the top. If I were to just sketch a density curve over the top of this histogram, that would give us an idea of kind of what the normal distribution might look like. And so as I sketch kind of a density curve here, we can see that this distribution is probably not best represented by a normal distribution. We have a skew to the right with unimodal, but we don't have that bell shape, and again we have the skewness here. So to say that this set of data is normally distributed or utilize a normal distribution to approximate values within this histogram really wouldn't be appropriate because of the non-normal feature that exists there, that strong skew to the right. Now let's take a look at our stem plot down below. Here we have an example of a back-to-back stem plot. And it really doesn't matter what the numbers are representing here. We just want to look at the distribution of the data. So let's start out on the female side. If we were to draw a density curve over this distribution, this would be something that we would consider normal. Now, just like our idea of symmetry back in chapter 1, we said we just wanted something to be roughly symmetric or approximately symmetric, well, we can kind of extend that same flexibility with the normal distribution. The female set of data here is by no means perfectly symmetric, but it is roughly symmetric, and it's roughly that bell-shaped curve there. And so this set of data, this female set of data, it doesn't contain any strong non-normal features, so we would consider this set of data normal. Excuse my writing here, I'm not very good with my stylus, so excuse my messy handwriting. All right, but again, the female set of data would be normal. The male set of data, on the other hand, is we take a look at the density curve there. Well, first off, we wouldn't consider this a strong bimodal, but it's definitely not containing one peak here. We have this little foothill off to the bottom, but we've got some gaps, we've got some possible outliers. The male data would definitely not be normal. Now, you females might be laughing because you already think males aren't normal, but that's not what we're discussing here. We're talking about the features of the distribution of the graph. And so as we look at those, again, we can see those non-normal features appearing in the graph. So this is good news to us. We know how to create histograms on our graphing calculator. Stem plots we know are very easy to create. So assessing for normality is something that's really pretty simple for us to do with the use of the technology that we have available to us. So this is one method for assessing for normality, but I want to introduce you to a new type of graph as well in our second method. Now, our second method for assessing normality is through the use of what's known as a normal probability plot. And basically what this does is it takes each individual data, converts it to its z-score, and then graphs these within a dot plot, basically, or a type of line graph, you might say. And so what we're looking for here in a normal probability plot, and what's extremely important, is that we're going to look and see that the points that are formed lie close to a straight line. Now again, notice it doesn't say lie perfectly in a straight line. We're not looking for our data to be perfectly normal. We're just looking for it to be approximately normal. So if it's close to that straight line, we're going to consider that data normally distributed. Okay? What we don't want to see, again, are systematic deviations from a straight line, outliers, which are points that fall away from the overall pattern of the plot, and also data that's strongly curved. And we're going to take a look at a couple of examples of normal probability plots here in a moment. But just note, the number one thing that we're looking for is that data falling close to a straight line. And again, our graphing calculators can help calculate these for us. So this is going to be a very helpful tool to us in assessing that concept of normality within a distribution. But let's take a look at a couple of examples. This first example of a normal probability plot is representing something that we hope to see within a normal distribution. Think of it as drawing in a line of best fit. If I kind of drew in a line of best fit here, that would be our straight line that we're trying to hit. And we can see that most of our points fall close to this pattern of a straight line. Again, they're not perfectly straight, so it's not a perfectly normal set of data, but it is a set of data that it would be appropriate for us to use a normal distribution in this setting because of most of the points falling close to a straight line. Now, we might want to kind of make note here. This set of data does contain a possible outlier. We kind of see this one point that's sitting out here, and that's kind of having an influence on that data. But we wouldn't consider it a strong outlier. As we can see, we're representing those z-scores down below, and notice that most of our values fall from -3 to +3, right? Even that possible outlier. And so again, we said that 99.7% of the data is going to fall within 3 standard deviations of the mean, and we're seeing that represented here on the normal probability plot. But the most important feature, again, is the fact that these points fall close to a straight line. Now let's look at an example of a normal probability plot that we would not consider normal. So in this normal probability plot, we can see a definite curve to our data. So if I were to try and draw a line of best fit through here, it might fit something like this. But we can see that those points really don't fall close to that line at all. In fact, this data would probably be better represented, again, with an exponential type graph or that curve to it. So this is an example where even though those values fall from 3 standard deviations below to 3 standard deviations above, the pattern that emerges within the plot is that of a curved distribution. Now, could we use a normal distribution to represent this data? We could. But again, we've said this before, there's a lot of things that we can do. That doesn't mean that we should do them. So this is an example where if we saw this in our normal probability plot, we definitely wouldn't want to utilize a normal distribution to represent this data because it really doesn't represent it well. So as we think about utilizing normal probability plots, again, it simply boils down to, is this data best represented by something that falls close to a straight line? And if we see that linear pattern to our data, that data would best be represented by a normal distribution. So in closing here, I hope you became aware of some of the basics of a normal distribution and also the idea of assessing for normality. If you're still struggling a little bit with the assessing of normality, I wouldn't stress too much about it. We want to introduce it here with normal distributions, but again, that's really going to become more important later on down the line. But that will be easy to understand then since we have a little bit of a background with it now. But what we really want to take away from this video are the concepts of the normal distribution. Those are what we're going to apply over the next couple of days as we begin to work some basic calculations utilizing that normal distribution. So don't forget to complete the form below the video, and I hope you have a great day. We'll see you soon.
Made with Doodlecast Pro.